Hello, everyone. This is a new episode or an IITT, this time on a very interesting subject. Well, they're all interesting, but this one I know I'm going to learn a lot from. Scour and Erosion, TC213 of the International Society of Soil Mechanics and Geotechnical Engineering. I'm Marc Ballouz. I'm the president, and I would love to show you what these experts know and tell us and learn a lot from this session. So I think this is the 20th episode. So we're almost covering half of all the technical committees of the society or the subspecialties. I'm going to share my screen to introduce our fantastic speakers. So with us today, we have Professor Shinji Sassa, Head of Soil Dynamics Group and Research Director, Port and Airport Research Institute, National Institute of Maritime, Port and Aviation. This is amazing. From Japan, you are the chair of TC213. I hope you will tell us a little bit about this technical committee and how active you are. Maybe some of our viewers will join you. And Dr. Cathy Avila, President of Avila and Associates. I'm guessing you are the owner of the consulting company. Vice Chair of TC213. Welcome aboard. Abutment Scour, Challenges at Bridges. Can't wait to hear you. Tiago, you're becoming the younger generation, so we're expecting newer intervention and ideas. Tiago Fazeres Ferradosa, Civil Engineer, Assistant Professor, FEUP and Coordinator Offshore Structures Foundation Unit. Neymar, CMAR, Portugal, they're scary, but you will tell us a little bit about it. Member of the TC, welcome aboard. And Mabel, my friend, originally from Lebanon, you are shining all over at the international scene. Thank you. You are also one of the organizers of all the IITT. I'm so happy today. It's your specialty. You're going to tell us more about your research. You're now a senior consultant, geotechnical engineer at WSP in New York, secretary of the Technical Oversight Committee of the International Society, and can't wait to hear you all. The floor is now with the chair of the TC, Shinji.
Okay, thank you.
Your turn
Thank
to
you,
share your
Marc.
screen. I'm gonna unshare.
For your okay.
I'm so excited, guys.
Can you say it? Okay.
Yes, perfect.
Okay.
Please, let's all mute so there's no interference. And we unmute when we want to interrupt nicely.
Okay. So thank you, Marc, the president, for your kind introduction. I'm Shinji Sassa, head of Soil Dynamics Group and research director at National Institute of Maritime, Port and Aviation Technology, Japan, serving as the chair of the technical committee on Scour and Erosion. I think our TC may be unique among all the technical committees of the ISSMGE because our TC involves both of geotechnical and hydraulic engineers. Indeed, the overarching theme of our TC is understanding of processes and design for protection and mitigation of scour and erosion through integration of hydraulics and geotechniques. Here, erosion means surface and internal erosion that pose significant risks to infrastructures and humans. As a consequence, the integration of hydraulics and geotechniques has been indispensable in advancing the field of scour and erosion. And in order to illustrate our TC activities, it would be best to show the agenda from our TC meeting that took place in September last year on the occasion of ICSE 11. We have been organizing the International Conference on Scour and Erosion series every 2 years worldwide. So I first showed the meeting outline as the TC chair, followed by a brief summary of the immediate past ICSE 10 that took place in Washington in 2021 by the TC Vice Chair Cathy Avila, She will talk later in this technical talk. And then they presented a summary and review of the TC special issue on Scour and Erosion of the International Journal of Geoengineering Case Histories of the ISSMGE. Here are global contributions across America, Europe, Asia, and Oceania, ranging from inland scour and erosion to river scour, coastal erosion, scour and internal erosion, and marine scour at around offshore structures were presented and summarized. I then presented the overview of the 20th International Conference on Soil Mechanics and Geotechnical Engineering session on scour and erosion. This was followed by the overview of ICSE11 by the conference chair, and introducing to ICSE12 that will take place in 2025, namely next year in China by the host. And the 4 years ahead of a particular ICSE, we determined the host by boats of that particular ICSE. And this time the host for the ICSE13 in 2027 was determined by boats, and it will take place in Portugal. And the co-chair will be Tiago Ferradosa. He will talk later in this technical talk. And we then discussed ISSMGE new initiative, Geoengineers Without Borders in the Face of Geodisasters, and followed by the introduction of some recent research programs and relevant information from some TC members. And as they presented concluding remarks for the TC meeting.
Do you all know what is GeoWeb? Sorry to interrupt.
I will show later. Yeah, I will talk about it later.
Okay, good.
Okay.
All right.
Okay. And I now like to highlight some recent major activities of TC during the COVID-19 period. We organized the first international TC virtual workshop on scour and erosion that was attended by 368 participants from 18 different countries worldwide in 2020. And we published the TC State of the Art and Practice book from Springer in 2021. We organized the first virtual ICSE10 conference in 2021 and also had the TC session in the ISSMGE in 2022. We contributed to the ISSMGE Time Capsule project in 2022, and as per the policy of the International Society, we started the open access publication of the ICSE proceedings in the online library of ISSMGE. This involved the ICSE10 proceedings as well as the ICSE11 proceedings in the years of 2022 to 2023. And we also published the journal special issue on scour and erosion in the IJGCH in 2023. And all of these activities are the first achievements of a TC on scour and erosion. I now like to show a very brief overview of these contents. We had the first TC virtual workshop on scour and erosion in 2020 and was attended by nearly 400 participants from 18 different countries. The local organizer was Indian Geotechnical Society, and the outcome was published in Springer Nature as part of lecture notes in civil engineering. The contents of this book reflect recent advances in the mechanics and countermeasures of scour and erosion, including coastal protection and erosion control and others. For the Time Capsule project, as milestone on scour and erosion, the 10th anniversary of International Conference on Scour and Erosion for the last 20 years, and we have some unique and distinguished standing in the ISSMGE ETCs in view of that multi-interdisciplinarity with both geotechnical and hydraulic engineers. And our International Conference on Scour and Erosion series publications involve guidelines with free access from worldwide researchers and practitioners. And we have been organizing virtual scour and erosion conferences and workshops in addition to the ICSE conference series that included young members. For example, the ISSMGE TC virtual workshop and ICSE10 in 2021. The ICSE11 took place in Denmark last year, and the ICSE12 will be organized in China in 2025 next year. So as I talked initially, we published a special issue on scour and erosion in 2023. I would now like to touch upon some relevant topics here. Jean-Marie Boulier, he's the past president of the ISSMGE and also the founding chair of the TC, presented a forward first. And then I presented a global perspective on Scour and Erosion as the editor and the chair of the TC. The contributions are from America, Europe, Asia, and Oceania, such that the Mabel et al. Presented a series of reliability analysis on the dynamic stability of Scour protections for offshore wind monopiles at 2 offshore wind farms, and Tiago will present topics along this line later in this technical talk. And recent rainfall, severe record-breaking rainfalls that took place in Queensland, Australia, caused extensive damages to the road networks in Australia owing to scour and erosion. And the interim and permanent remediation measures adopted ensured particularly the highway's status as open and safe and are projected to be effective in the face of ongoing global climate change-induced, particularly intensification of rainstorms. Tsubokawa et al. Presented simultaneous wave-induced surface erosion, scour, and internal erosion around the retaining wall that caused the collapse disasters of coastal road slopes, and an effective countermeasure such as filter layers was presented. I'll touch upon these topics later in my talk. And Cathy Avila presented 40 years long analysis of the stability of bridge subjected to undergoing scour, and she presented 3 different types of countermeasures: hydraulic, structural, and monitoring measures that kept the bridge stable and open to the traveling public. Cathy will also talk about this topic later in this technical talk. Harris et al. Presented scour prediction in cohesive marine soils. A so-called hybrid approach was presented, field data combined with laboratory soil erosion testing. As for the laboratory and in-situ soil erosion testing, Mabel will talk about this topic later in this technical talk. And here is the hybrid approach combining the field data and the laboratory erosion testing led to improved evidence-based set of scour estimates that benefited the projects of offshore foundations. And Shan et al. Presented combined geotechnical site investigations, a laboratory element test, hydraulic flume test, and advanced numerical modeling led to the more cost-effective design of foundations in a bridge replacement project in USA. So for the new initiative of the ISSMGE Geoengineers Without Borders that explained briefly in this slide, all TC members agreed and would be happy to contribute to this new initiative when such incidents occurs worldwide pertaining to a scour and erosion. Is it okay, Marc?
Yes.
Yeah, okay.
So the idea,
Yeah.
and this is not only for you, but all our viewers and all the TCs, hopefully they're watching.
Yeah.
I started this idea at the image of Médecins Sans Frontières. So wherever there is a disaster, we send our engineers not to teach them, not to just be experts, but to show solidarity as one family worldwide, geotechnical family, to help with the reconnaissance, put our brains together. So this is the initiative that was a dream that now became reality. And the first in-person missions were at the floods and landslides in Brazil with Fernando Marino, and the second one was in New Guinea with the big landslides, and in both disasters, many deaths. And in New Guinea, Juan, what's his name, Copac was there, and we published their work and talked about those missions in the bulletin. So I invite all the TCs to be volunteers, and the head of this project we call a GeoWeb is Professor Pierre Delage.
Okay.
So thank you
Okay.
for mentioning it here. It's
Yeah.
really touching me. Go ahead.
Yeah, all that members of TC on Scour and Erosion would be happy to contribute this initiative. Thank you, Mark. And I would now like to talk about some recent advances in mechanics and countermeasures of Scour and Erosion from my own keynotes that took place in September last year, and also the former ones. Here I'm showing the effect of overflow and seepage coupling on Scour. Here, tsunami, overflow, and seepage coupling actions induced a score of the mound of the caisson breakwaters, as well as seabed ground, that caused bearing capacity failure, leading to flow of the mound, resulting in the total failure of the caisson breakwater, which otherwise remained stable without the coupling effect. That means without seepage, the overflow only induced score did not lead to the destabilization of the breakwater. However, the coupling actions of the seepage and overflow led to the total failure of the breakwaters. So such new knowledge has been utilized for the design of tsunami-resistant breakwaters with embankment, where the embankment reinforces the caisson against the tsunami wave force, and also substantially suppresses the effect of the coupled overflow and seepage actions on score of the breakwaters. Such structures are for preparing for the megathrust earthquake tsunamis that are expected to occur in the near future, particularly in Japan, also in the Pacific Ocean. So erosion research has led to some groundbreaking discovery on fundamental soil mechanics, that is in porosity of sands. Sand relative density changes normally from 0 to 100%. Here, the dynamics of suction at waterfront areas subject to cyclic exposure and submergence indeed undergoes remarkably wide range of sand porosity evolutions, over 200% variations in terms of relative densities achieved, from giving rise to from very dense to very, very loose, such as giving rise to bubbly sands seen across the globe, as shown on the left on this slide. So such new knowledge has been also used for a novel engineering design of coastal land reclamation. The top right figures on this slide show that in 3 months following reclamation, the coastal reclaimed land underwent dynamic movement under waves and currents. However, the situation has substantially changed in the subsequent 3 months. Namely, the coastal reclaimed land became distinctly stable owing to the feedback and interplay between sand porosity evolutions and erosion. The red dotted line here shows the predicted stabilized height based on the developed analytical framework that takes account of the interaction of such hydrogeodynamic effects and processes that are shown to be consistent with the observation. So another important facet of the score and erosion is internal erosion. I'm showing here cavity collapses seen across the globe behind seawalls. Particularly, the photograph on the bottom left shows the site of a fatal accident where a cavity formed in the backfill behind the caisson suddenly collapsed without giving any alarming signs to the soil surface. That means leading to a fatal accident on site. So the prototype scale visualizing system allows us to...
Can you go back one slide?
One slide, okay, this one? Okay.
Yeah, they looks like sinkholes. And look what I
Yeah,
noticed. If you look on the left picture at the bottom,
yes,
you
this
see
one. Yeah.
that the depression happened at the joint of the
Yes,
caisson.
that one, the caisson joint, yes. The caisson joint has some defect, and through this caisson joint, sand migration occurs, and then the
Wow.
cavity develops above the groundwater level because the sands are inherently cohesionless, so no suction, no cohesion. But above groundwater level, sand has essential cohesion due to the development of suction, so a cavity can stand by itself above the groundwater level. So the cavity gradually grows and develops around until reaching the about 2 meter or 3 meter
Sudden collapse, yeah.
and suddenly collapsed without giving any alarming signs to the soil staff. So the fatal accident occurred. So this occurred worldwide recently. So I'll touch upon it later. And such incidents, the prototype scale visualization system, that we can see the cross-sectional view of the entire soil, including cavity, and can investigate the simultaneous processes of internal erosion and collapse, as well as examining the performance of the countermeasures, such as filter layers, against diverse forcing conditions involving tides, storm surges, rapid drawdown, waves, rainfalls, and overtopping. And this led to Nobel filter criteria for preventing internal erosion against dynamic forcing conditions. The criteria have proven effective in ensuring the safety of important infrastructures such as airports, revetment, quay walls, and sea walls of, as Mark said, of sandy beaches, both natural and artificial sandy beaches, that led to recent fatal incidents worldwide. But these filter criteria have suppressed, indeed, and prevented the occurrence of such collapses and diverse forcing conditions that involve waves, tides, and seepage flows, seismic motions, and overtoppings and rainfalls. So in your TC, the cross-disciplinary integration of hydraulic and geotechniques has indeed played a vital role in advancing the field of scour and erosion, which pose significant risks to infrastructures as well as to human beings. So that's all for my summary of our TC, and followed by the three eminent researchers. So that's all for my talk. Thank you.
Yeah, Mark, do you mind if I pose a question?
Okay.
Yes, of course. Go ahead.
Yeah, of course.
Hi, Shinji. So just looking at the new criteria that you presented, which is very interesting and useful, how useful it could be, for example, in offshore situations where we have cyclic motion of waves on top of with larger water depths, perhaps non-breaking waves.
Okay. As I show in this slide, there are three types of filter criteria. One is for earth dams, and second one is for the scour and erosion civil sand in open seas. Maybe Tiago is talking about this criteria. I think the new criteria is particularly for preventing internal erosion backfilling sand behind coastal structures. So in offshore areas, maybe the open filter is particularly used, but of course, for preventing internal erosion backfilling sand can be also utilized for offshore applications, and in such cases, but we need to be careful about that this is a filter layer consisting of two layers, upper layer and lower layer, but the structure or the stratigraphy might be different between the offshore use and use for the interface between sea and land. So, but the basic concept can be applicable to offshore areas. This was published in Coastal Engineering in 2021. So, Tiago, you can have a look at our paper that was published in 2021 in Coastal Engineering.
Yeah, because it could be interesting, for example, in a lot of the studies we do on the filter interaction with the upper armor layer of scar protections, and particularly in those riprap solutions, because often we have a lot of problems of filters.
Please have a look at the 2021 Coastal Engineering paper.
Very interesting. Thank you, Shinji.
Thank you.
This is very nice, Shinji. I'm impressed by how active your technical committee is. Thank you so much.
Okay, so I stop sharing. Okay.
Yeah, you can stop sharing.
Okay. So maybe the Cathy will follow this talk.
I want to tell you that I have the visa to China. So you come from Japan and I meet you in China for the next conference in 2025. So make sure you invite me.
Yeah. Okay. I can. Okay.
Katie, the floor is yours. I see you already started sharing. Can't wait to hear you. If we all mute our mics, go ahead, Presidente.
There we go. Now you can hear me. Thank you very much for the opportunity to present at the ITT. I appreciate it. I am more of a practitioner than a researcher, so we'll talk a little bit about abutment scour and lateral migration at bridges. I'm going to look mostly at abutments, not at piers, though you may see a pier or two, just to make sure we're all on the same page, because not everybody gets the opportunity to work with bridges. We'll just talk about the parts of a bridge. So we'll start out with here's the deck, the pier, the footing. Sometimes we have piles, sometimes we don't. Generally, we call it a spread footing, not on piles, but sometimes they'll just call it a footing. This is our abutment 1, pier 2, pier 3, pier 4. That would make that span 1, span 2, span 3. So now that we're all bridge engineers, going to talk about abutment and abutment washouts. If we look here at the abutment on Interstate 10, what we call Tex Wash, we can see an abutment scour failure. This bridge actually had quite a bit of rock riprap around it, protecting it, but the abutment was founded on spread footings on alluvial material without any piles underneath it, so it had some vulnerabilities. This fell down probably about 5 years ago, and all the bridges on I-10 that had similar features are being retrofit at the present time. I'm going to talk mostly about the atmospheric rivers that California experienced in March of 2023. And specifically, I'm going to look at a couple of projects in Tulare County. Tulare County's down here. If we looked at Fresno, that is the centroid of California. If you kind of put your finger up and put a map of California and spun it around, you would see that the literal center or centroid of California is somewhere in Fresno. So we're just a little bit south of there. In general, Fresno County has 2/3 of its area in very mountainous areas and about 1/3 of it in flat land, very big agricultural area. And this shows a map of the damage sites that occurred in that March storm event. Going to start with the road D60 on Cross Creek. We're almost to the flatlands here with Cross Creek. And if we show a quick movie, what we see is some broken concrete riprap over here at this abutment. But let's look at the opposite abutment, because that's the interesting one. So if we zoom in here, we see these abutment piles, and we see the erosion going on along with the almost vertical embankments over here. What did we do about that? Well, here's a nice still photo after the event had stopped, and we see the piles, but we also see something quite alarming out here, where we can see some daylight under here. And as Dr. Sassa just talked about, sometimes you get some catastrophic failures that you can't see. This was fortunately a catastrophic failure or we did not get a catastrophic failure and we could see it. So this is somebody standing on top of the ground up here. You never want to see cutouts in your asphaltic concrete. You really don't want to see big cutouts in your asphaltic concrete. Here's the piles that are going down, and you can see the water. They shut down the road and did a scour countermeasure. We can see our person scale here. They put some plates on to a slope, and if we look down, we can see our person scale here. They floated some concrete. There's our pile underneath that abutment, and here it is as it came up. And finally, when all was done, they pulled the forms, and we had a pretty robust abutment scour countermeasure. The next one we're going to look at is going to be Globe Drive. This is the Upper Tule River. Get an idea of what kind of recurrence interval we had for this event. We looked at a 17C plot of the gauge, and what we found was that there was 13,400 CFS that occurred, peaked in March 10th. For those of you who don't speak English, 380 QMEX. And that was just under a 50-year event for that particular gauge. So we're not talking necessarily a really huge event, but nothing too small either. We did a bit of hydraulic modeling with HEC-RAS for this location, and we can see here that for this 94-foot long bridge, 28 meters, that's our 28-meter bridge right here inside of a 200-meter wide floodplain. So this, just want to point out, is our approximate bedrock profile. And we see that we have spread footings, nothing below them, but they are embedded into that bedrock profile. That's going to make a difference as to how this bridge performed in that flood event. We see a lot of debris that got caught up on the bridge. We see floating debris here. We also see rolling debris here. So we actually had both the rolling debris. These are 1 meter-ish big boulders. So no slack when it came to how much velocity it took Mother Nature to utilize to get those rocks to move. Bird's eye view of the bridge. We can see the bridge is actually looking pretty good, but we lost all the embankment flow around here and around here. So what did they do? Took a bunch of excavators. This is what it looked like before. That's what it looks like today. They were able to basically put back in what they had before. Are those roadway embankments still vulnerable to scour? Yes. But in general, there's not a very large ADT out here, average daily traffic. And so when there are large flood events, people don't tend to be on the roads out here. Third example, Deer Creek on Mountain Road 112. Again, had the joy of having a gauge out here from the USGS. So 4,500-ish CFS was our peak, 127 QMEX. That really was a 50-year event. So we're finding that at least up in the mountains, we had about a 50-year event. This lovely bridge here, 2-span bridge, span 1, span 2, didn't look so good after the flood event. If we look, we can see that that deck looked pretty cattywampus after that flood event. So we had some pier scour. But the bigger challenge, if we look at this not very long bridge, if we look at that in plan view from Google Earth, we see it was 16 meters for the old bridge. And that old bridge had a pier that wasn't founded on was founded on alluvial material, nothing bedrocky about it. And here's what it looked like after the flood event. That went to a 67-meter wide channel. And maybe because there was some debris caught up in the bridge, it outflanked it. We don't know for sure. There was a temporary bridge that was put in. That's only 18 meters. That temporary bridge looks like this. We can see some rock riprap around the embankment. If we look at the as-built plans for that particular bridge, we do see that it does have spread footings without being on any piles. So it has some vulnerabilities, but it is a temporary bridge, not expected to stick around for a heck of a long time. And we also see that the channel, these roadway profile coming up to it, the embankment fills, which you can see here, are blocking the flow and causing a bit of backwater upstream, more this side than that side. So there's been a lot of excellent guidance that's actually been put out by the Federal Highway Administration, FHWA, on protecting abutments from scour. And riprap has been the historic thing that has been used. Also looking at some of the flow training works, bendway weirs and the like, in order to try and kind of convince Mother Nature that she wants to go in the direction we want her to go in and not outflank the bridge. So that looks like that in real life. So there's 3 publications that are used in scour in the US, and I know they're also used outside of the US. Those are actually being updated, so we're looking forward to that. First, the 2012 publication of HEC 18, Evaluating Scour at Bridges. This is going to be the last one to be updated. I understand about a year out from updating it. The 2012 version of HEC 20, which is Stream Stability at Highway Structures, should be updated next or shortly. And finally, the HEC 23, which is Bridge Scour and Stream Instability Countermeasures. That one has already been updated. Some advanced copies have gone out, and that should be coming out to the Federal Highway Administration's website, which you can utilize to download any of their publications. And I don't know if you guys have any questions.
Katie,
I have one question. The Road 60 in Tulare Country, when we saw the daylight behind the abutment, was that a slope stability failure of the embankment?
I think it was more of an erosion failure, because as we look, boom, go back one more. If we look at the movie, gosh, what we actually see is erosion, Mother Nature eating away from the bottom, and then you'd see that, I don't know what geotechs call it, God bless you, but basically you're eroding the toe, dropping that soil in, eroding the toe, dropping the soil in. What would you call that?
Basically, it's a type of slope stability, because eroding the bottom, meaning increasing the height of the embankment and making the slope steeper, so it would just slough and you would lose big chunks. Part of local stability failure. That's very interesting. Yeah.
Katie, thank you so much. You and I connect by being both practitioners, so I really like your examples. Thank you so much. I leave the floor now to our next presenter, Tiago.
Hi again, Marc. Let me check if I can share my screen.
Share your screen with big slides.
I guess you're seeing them now, correct?
Perfect, yes.
Yeah, okay. So jumping a little bit off from inland towards to the outer sea, to offshore, I'm going to try to present you a little bit the challenges of scour and scour protection in offshore environments. One of the things that differs a lot from the fluvial environment is that a lot of the failure cases and the mechanisms of failure and the cases of failure that we are aware of are often very confidential, and they're very hard to see, because when a bridge fails, you see it's inland, but in offshore situations, there is a lot of secrecy from the industry. Yes, there are a lot. Sorry, you guys, I lost my slide here. There are a lot of failures or problems going on in Scour that you don't actually see. Why aren't
Should
you
start
guys...
from the beginning. Start from the beginning. You're starting
sorry.
with the last slide.
Apologies,
They are the
Marc.
same
Okay.
slides, but one says thank you.
Yeah, thank you. There you go. Now,
here we go.
So we are the NEMAR group. It's the marine energy group. The Scour problem, as Shinji already pointed out, it's a mixture between geotechnics and hydraulics. We deal a lot with hydraulic problems. One of them is scour and scour protection, with a lot of physical modeling and numerical modeling as well, including for industry applications, but also in research and academia. Now, one of the challenges that I would like to point out that remains a key challenge for the upcoming years is the complex geometries one. And this is a very important one, because with the growing of the offshore wind market, the novel marine energy structures that are being placed at sea, or at the very least studied, and the demonstration projects on such structures imply a lot of complex geometries. And when you jump into complex geometries with complex flows, combination of waves and currents, tidal velocities, and so on, then it becomes really, really difficult to make predictions on scour and to understand the problem itself. So this would be one of the challenges that I would point out, with major develops still to be made in the upcoming future. Now, and this includes the J-tubes, the pile sleeves in jackets, the crossing cables, the manifolds. So you can imagine all of these structures that you may have with complex geometries and complex flows. And why is that a big problem? Because unlike the methodologies that we have been seeing being published for bridges and so on, in offshore engineering, the methodologies and the norms and the standards for scour still lack a little bit of development on a lot of these tricky situations. So we know a lot about scour on monopiles, how to deal with them, etc. We try to convert a lot of those complex cases into equivalent monopile cases, try to use factors in order to account for the transparency of the structure, or perhaps trying to account for the amplification factor that might be higher than in a simple monopile. But there are no end-stated rules, if one can say so. It's a little bit of a gray area where the designer's experience is worth a lot, and then the physical modeling is required, and so on. So this remains a big problem, and this challenge of complex geometries and complex flows is very much also in the basis of the need that we have to advance with the standards and norms. We apply a lot of the knowledge that comes from fluvial, but still it's not enough to account for all the problems. Then with the growing situation on offshore wind, but also on aquaculture in offshore locations, tidal energy, wave energy, we start to put more and more structures. We start to look for co-location of these structures, perhaps aquaculture with offshore wind or wave energy with offshore wind. And that moves that we start to have moving elements around fixed foundations, bottom fixed foundations, sometimes floating foundations, where we know that the cyclic movement of the cables can induce, for example, liquefaction or even increase the scour at the anchors, depending on the water depth, of course. If it is not too large, that scour can be neglectable. So with this increasing complexity and with the added co-location of these structures, scour becomes a huge problem. And then what we do a lot in our group, and this is one of the most recent cases that we studied, is the combination of, for example, wave energy devices located at the bottom, and how the scour patterns may change, the amplification of the shear stresses may change around the monopile, for example, for an offshore wind turbine or a gravity-based foundation, how, for example, the pressure or the velocities column in heights can change, and how the pressure can change upon the armor layer. So all these things that pose numerous things that we are not still quite sure on what's happening, and uncertainty on top of the problem. So that also remains a key challenge. Now, additionally, just to make it a little bit more complex, we want to look for novel concepts for scour protections. Why? A lot of them are related to the need to enhance biodiversity. Some of them are more related with the fact that we want to avoid, for example, systems that have plastic in it, to avoid microplastics at sea. Although we want to, for example, protect a structure from scour using an artificial seagrass, now we wanted to make it more eco-friendly, with eco-friendly materials, with eco-friendly shapes. All of this, again, changes roughnesses, changes the interactions with the flow, changes the type of geometry, material, and so on. So all these novel concepts, and some of them have been proved to be quite useful and quite nature-friendly, they are still very uncertain in their performance. So this is another challenge that we still have a lot to do on. If you want to have a look at recent developments and novel concepts on this, the paper that we present below, it provides you a summary, a very recent summary. Then, because we also need a lot of physical modeling to study these complex situations, we need to quantify damage at those scour protections. But again, to quantify damages at these scour protections, we also need better methods, new techniques, better testing. So another challenge that falls on top of this is the actual quantification of damage. The one that you see here is a small example where we look at ripraps with dynamic equilibrium, so they can have a little bit of movement, but not so excessive that exposes the filter layer. And in this methodology, it was introduced by de Boon some years ago. The criteria was that the filter exposure could not be above the equivalent size or the equivalent area of a 2x2 stone square, okay? For the armor layer. We recently developed the method. We've been studying that. It has a little bit of probabilistic background combined with physical modeling that actually proved that visual criteria introduced in the former days was actually correct. The damage evaluation at the protection, at dynamic scour protections, the failure criteria tends to stabilize for that value. So this means that there is still a lot of things to be done concerning the actual academic research on methodologies to quantify the damage in physical models that we often use for the industry in offshore engineering cases. Now, for the design itself, we keep on struggling with improving our design, trying to improve the norms and so on. A key area of research lately has been the probabilistic design, probabilistic-based design methods. What's the problem with this? Scour is such a random process, and scour protections, for example, riprap scour protections and other concepts, they are so random in their nature that it's not the same thing as designing, for example, a concrete slab or a pile where you know that the resistance is X and the momentum shall be epsilon or Z or whatever. So the thing here is that for such a random process, it's also very difficult to actually provide probabilistic-based design methods, but it has been an area, a key research area, still a bit in the beginning, but developed a lot lately with the AI models, the artificial intelligence models, and the machine learning techniques and so on. Still combined with physical and numerical modeling, but there have been some quite recent contributions on the relationship between the probability of failure of a scour protection concept and the variables that control the scour process and mechanism. And in some cases, we can even use those methodologies, for example, to develop scour risk maps, as you would do for a set of bridges or a set of piles in a bridge. We can also do them, for example, for offshore wind farms or wave energy farms or aquaculture farms, whatever type of structures that you may place at sea several times in the same location. So that's another challenge, which is something that might be proved to be quite useful in practical applications. Then again, another thing that has been lately developed a lot is the study on the interaction between not only the soil, the structure, and the flow, but also the scour protection and the structure itself, including the flow, of course. But the way that the scour protection or whatever concept that you may use can add or may change the stiffness at the interface between the soil and the structure, that's something that we have been seeing a lot over the last, say, 4 to 3 years in offshore engineering publications and research. So that's a very important area. There are even some studies on how a scour protection may add a little bit of stiffness in monopiles that have been installed and registered more vibration in the natural frequency, for example, than one would expect. So a lot of things to be done in this matter as well. And still on the basis of numerical modeling, and this is almost, I would say, the final challenge that I would like to highlight in what comes to offshore engineering is the actual numerical modeling of scour protections itself. So we do a lot of numerical modeling on scour with waves, with currents, so that's pretty well established. Of course, there is always something new to be done, but that's something that we studied a lot. Now, when it comes to study the protection behavior itself, not only the pore pressure inside of it, but also the movements of the stones in the armor layer, the failure mechanisms, the erosion, or the flow slide at the armor layer, or the edge scour, then it becomes a very, very tricky problem because it's a very time consumption and it requires a lot of computational, computational power. So this is still an area where we lack to see a lot of developments lately, and we expect it to grow in the upcoming years. A lot of the sets of publications that we've been seeing out there, they try to combine porous media approach with single sphere modeling, try to divide layers of the scour protection in these two types of modeling, but still a lot to be done. And it's a problem that may register a lot of developments now that the computational power is no longer such a big problem as it used to be in the past with the supercomputers. Nowadays, universities are developing a lot of work on this. Now, with this being said, and just to rest my case, with all of these nice problems, with all of these complex situations, we still don't know a lot of things that go back to the basics of scour. In the last conference that Shinji just mentioned from the TC213, so the conference that was held in Denmark, one of the key ideas was this: we still have a lot to do on the turbulence effects, the scouring layered soils, for example, or mixed soils, the scouring cohesive and non-cohesive soils. So a lot of things that go back to the basics of scour that we still need to do a lot of research on, that are actually the basis for all of these problems. So if you guys want to have a little bit of scour research or scour practice in the industry, I'm pretty sure that you will have a lot to do in the upcoming years. Wouldn't you say so, Marc? Thank you.
I really like your conclusion. The more we know, basically, it's the more we know, the more we know we don't know. Very
That's
nice,
true.
very nice presentation, Tiago. Mabel, the
Yes.
floor is yours.
Can you see my screen?
Yeah.
We can see your screen, yes.
Thank you. First of all, I want to thank you for having me at the other side. It's a pleasure to participate in one of the IITTs. I worked on the topic of soil erosion and bridge scour during my PhD years at Texas A&M with Jean-Louis Bruyot. And we tackled together many soil erosion problems, including bridge scour at abutment that Cathy covered. We did levee overtopping, internal erosion of earth dams, and meander migration. And we always found that soil erosion testing, which is the topic of this presentation, plays a key role in characterizing soil erodibility and better understanding and resolving the problem at hand. So we're going to talk about soil erosion testing here. First things first, let's go back to the basic, following Tiago's advice right away. Every soil erosion problem has three components into it. We have the soil or rock, we have water, and we have the geometry of the obstacle that the water is interacting with. So the soil is described by its erodibility, the water by the velocity or the interface hydraulic shear stress, and the geometry of the obstacle is quantified by the obstacle dimensions. Now, from the point of view of soil, soil erodibility can be defined by the relationship between the erosion rate of that soil or of the soil surface and the velocity or the shear stress. And this is what we call the soil erosion function. And the soil erosion function can be seen as a fundamental constitutive law for any soil erosion problem, much like the stress strain curve, for example, is the constitutive law for soil deformation problems. And what does erosion function look like? We can see here that we have always on the y-axis the erosion rate. On the x-axis, we could either have the velocity or the shear stress. And normally when we plot the erosion function of a soil, it will typically follow one of these erosion categories from 1 to 6 here that were developed by Jean-Louis based on 25 plus years of soil erosion testing experience. And we can see that these erosion categories kind of relate the USCS classification of the soil to its erosion category. So it gives a very good first idea of how resistant the soil is to erosion. But for sure, there's no replacement of soil testing in order to get the actual erosion function of that specific soil. And this is where we get to this list of the most commonly used erosion tests in practice and in research today. And the development of these tests has taken 50 years plus for the lab test and around 10 years for the field test. In the lab for surface erosion, we have the erosion function apparatus or the EFA and other flume tests like the ASTD, the ASSET, the set flume, the SURF. For internal erosion, we have the hole erosion test and the slot erosion test, which are the evolution of the pinhole and the drill hole test. Now in the field, we can see that we have much fewer tests. And most recently, we worked on the borehole erosion test, or the BET, which was a part of my PhD research. And The PET is a very simple test. It requires no special equipment, no special expertise. It gives the erodibility profile of a soil along the depths of a borehole. And while developing these tests, we took some samples from the same hole where we performed the BET. We went back to the lab, performed the EFA, and compared the result. And the remaining slides here will talk about the EFA, the BET, and will show how these two tests are in fact complementary. So first, the EFA. The EFA test consists of pushing a soil sample at the bottom of the conduit at a speed that is just enough or just equal to the speed of the soil erosion. So we can then estimate the erosion rate as being the rate of the advancement of the piston. So for each velocity of the water flowing in that conduit, we can estimate the soil erosion rates, and point by point, we can build the erosion function in terms of velocity. And we can even go from the measured mean velocity to the shear stresses using Moody's chart, and we can have the erosion rate and function of shear stresses as the final outcome of the EFA. And here we can play a video, for example, of demonstrating the EFA on a silty soil sample. We see that at the velocity of 0.35 meter per second, there's an erosion rate, and then the erosion rate increased significantly at the velocity of 0.55 meter per second. So this is the EFA. Now moving to the field test, the borehole erosion test. This test, I think, it has been performed so many times before without us knowing, just by drilling boreholes for the purpose of soil investigation and using the wet rotary drilling, which is the most common used technique for drilling in the US. Here, basically, you have the drill bit at the bottom of hollow drill rods, and you have drilling fluid circulating down in the drill rods. So as the drill bit is cutting the soil cuttings are moved or are returning up to the surface in this drilling fluid. And if the velocity of the drilling fluid is higher than the critical velocity of the soil, then this is an erosion process because the drilling fluid is eroding the side of the borehole, resulting in the increase of the diameter of the borehole. And we can go from increase in diameter to the erosion function by actually calculating the erosion rate of the soil and estimating that particular velocity.
You don't need to drill anymore, just push.
Right? So the procedure is very
fracking.
simple.
It becomes fracking.
Yeah.
Keep going.
The procedure is very simple. Like I said, we start by drilling a hole. A 100 millimeter diameter is enough. The depth is should cover the entire depth of interest of the soil. After drilling the hole, we remove the drill bit and the drilling rod, and we lower a caliper, could be a mechanical caliper like in this picture, down the bottom of the hole. And then as we pull out the caliper, we're actually getting the initial reading of that diameter. After that, we reintroduce the drill bit, the drilling rod, and we circulate water at a certain velocity, a selected velocity. And that velocity of the flow would erode the borehole. We would increase the diameter of the borehole. So after, let's say, 10 minutes of flow circulation, we remove the drill bit and we measure again the diameter profile using the caliper. And we can repeat these steps and circulate as many velocity runs as we want in order to get the erosion function of the soil. So the equipment is nothing more than a drill rig, a mechanical caliper, and for the water circulation, we use the pump on the drill rig, an inline flow meter, and a stopwatch in order to just record the time of the water circulation. So we performed at the Texas A&M site. We have a clay site, we have a sand site, and we performed a series, maybe 4 BETs in each site. And this slide here shows the flow and velocity condition for each of the BET tests. In terms of showing the results, we can show how the diameter profile increases after each velocity run. So for example, let's focus on the clay side example. You can see that C0, or the initial diameter reading, gave us about 95 millimeter for a diameter. And then after the first velocity run, C1 is now about 99 millimeters. So the increase in diameter was 4 millimeter. The increase in radius is 2 millimeter over 10 minutes of flow. So this is an erosion rate of 14 millimeter per hour, for example. That is corresponding to that first velocity, which was if I'm not mistaken, 0.4 meter per second. So this is the first point on the erosion function. We can also show the erosion rate profile along the depths of the borehole. And here we can conclude that different soil layers have different erosion rates. And in order to estimate the shear stresses, because we've been talking about velocity and the velocity of the flow. So for us to get an idea of the shear stresses along the side of the borehole and at the bottom of the borehole, and to get a better idea of how the flow is being distributed and how the velocity distribution is, we did computational fluid dynamic modeling using the FANS numerical method. So this is the geometry of the borehole that we used. We simulated two flow rates, a low one and a higher one, and we considered three distances between the discharge point and the bottom of the borehole, and two cases for roughness, a smooth and a 5% roughness hole. So this is, for example, how the velocity is distributed at a certain time step. This time step corresponds to 37 seconds after the initiation of the flow. For the low flow rate, the lowest gap considered, and the rough case. And here we get the shear stresses. So we can see that on the left, we have the shear stresses on the side of the borehole. And we can see that after 0.4 meters above that discharge point, the shear stress is stable. And it seems here it's 0, but for that flow rate, that is the lowest flow rate, it's between 0.5 and 1 Pascal. And this actually goes to 10 Pascal for the higher flow rate. Of course, it's much lesser than the shear stress on the right here, which is the shear stress distribution at the bottom of the hole. And actually now that at that point, we kind of realize that we have two shear stresses, one at the top, one on the sides, and one at the bottom, we kind of realize that there are two erosion processes happening. So the general BET, we call it now the lateral borehole erosion test, and it's the increase in diameter because of that side shear stresses on the borehole. But we also have the bottom borehole erosion test, which is also after each velocity run, the caliper data show us that the borehole is increasing in depth. So this is because of the bottom shear stresses. We can also calculate that rate of increase in depth, and we can get erosion function as well from the bottom borehole erosion test, which is much more like a jet test. And finally, a quick comparison of the EFA, BBET, and LBET. We plot the erosion function of the same borehole and of samples tested in the EFA from the same borehole on one erosion function for the clay and for the sand here. And we can say that the erosion function are kind of aligned, and we can conclude that more or less we can say that the three tests are reasonably in agreement. There is, of course, some scatter due to the accuracy level of each of the tests, but overall, it is looking good. And finally, I would like to end with a picture of me and Jean-Louis climbing Teton Dam to take some samples to test them in the EFA. And this is a dam that failed, and this is a very steep slope. So I'm showing the picture of us standing there, but there are actually videos of us going back to the ground level. We were using our hands and our feet. It was something for sure.
The field is always amazing, and we have a lot in common, Mabel. So we both studied at A&M, we both come originally from Lebanon, and we both have Jean-Louis as our chair in PhD. That's so good. Thank you for being with us. You can stop sharing. This has been an amazing talk. Well, Katie, you mentioned that some 1 meter diameter rocks were flowing downstream. I want to tell you, I live on Bee Creek in Austin, Texas. And one time, because of the heavy rains and floods, I witnessed a Hyundai car flowing in the stream. And that's like 5 meters. downstream, maybe more than 1 mile before it hit the rock here and stopped, where the creek widens and the flow gets slower. So I really appreciate your input. Shinji, you showed how active the TC is. So
Thank you.
you are an example to all the TCs. Thank you so much. Hope to see you in China in the next conference. Also, you mentioned.
Okay, Marc,
mentioned,
can you really join our ISSMGE conference in China next year? Can you really join?
Yes, I can.
Yes,
Yes, of course.
It will take place in November 4 to 7. Are you available?
I will make myself available.
Okay.
Just to let you know, I toured
Okay.
35 countries in 2 years. That's my mission.
Okay.
35 countries in 2 years.
Okay, so
175 events, including this one.
Okay.
Between online and in person, 175 events in 2 years. So I'm a pretty active president.
Okay. Thank you for your.
And thank you for also being active with the HTC Heritage Time Capsule. It's growing. We now have HTC website separated from the ISSMGE, which accepts material from all different languages. We're going to have a physical time capsule. So HTC stands for Heritage Time Capsule. We're going to have a physical time capsule that will be placed in during the conference in Vienna, the international conference in 2026. They're going to give us a permanent location in the museum they are establishing for Carl Terzaghi. That's where it all began. And that time capsule will be closed for 100 years so that our children can check what we used to do. So Heritage Time Capsule is growing. Also, you mentioned being active with the Journal of Case Histories. I have good news for all our viewers. We are establishing a new publication committee that will launch a new journal, which includes advance in research, like Tiago was showing the future. So now anyone can come to ISSMGE, and hopefully it will be the leading publication destination. So we will have 2 journals, one on case histories that you can present, and one for research advances and innovation. Hopefully it will be one of the legacy of this term and my presidency. It's a dream, hopefully that will come true by next year. What else I want to tell you? Tiago, you mentioned model flows and design with movements. What software are you using? That's pretty advanced.
I would say, how many softwares are we using? Because it's a really tough one.
Guessing
so,
with checking natural frequency, this is really advanced stuff.
Yeah. So it's right now it's a coupling of modeling between different softwares and then trying to put everything together in the same pan and try to cook it as much as we can.
Don't worry, you don't have to answer. I'll come to you.
Okay. No, but mostly Reef 3D combined with Flow 3D, OpenFOAM, all of those. That's what we use the most. Yeah. And SPH for single sphere modeling. That's pretty much all of those.
Nice. Katie, you proved how important the subject by showing in one county, one event, how many failures. So this can be considered a geodisaster. When do you say this is a geodisaster? When authorities are overwhelmed in intervening and solving problems. So thank you for showing how important the subject is, and we should take it really seriously as geotechnical engineers and hydraulic engineers.
The county staff was out there just working tirelessly to open up the structures as quickly as possible. I don't think they slept.
Like an earthquake,
that
basically.
time. Yeah.
Yeah, it's like a local earthquake. I want to tell you a story. I was involved with a project in France at the Pointe du Hoc Cliffs. And the problem was at Pointe du Hoc is where D-Day happened. One day before D-Day, maybe you know the story where the Green Berets started climbing the cliffs to neutralize the artillery of the German army, and the observation post at the time became now a museum. But then a few years ago, that museum started cracking, and the rocky cliffs, if you compare Google Earth photos from or satellite photos from 40 years ago, you see the rate of erosion of the rocky cliffs. So, and it's due, and I'm trying to answer Mabel, is it an erosion or a landslide? So it starts as an erosion at the bottom, but then the vertical cliff can no longer hold this cantilever, and you see a lot of debris, and we walked on the shore. So the wave action, if you look at the graphs that Mabel showed, how the rocky is category 6 or something, but with time, it's just a matter of time. So erosion is happening all the time around us. And I have a question for all of you. When does erosion become a landslide? Where do you draw the line? Is it a surface landslide, or that's a nice question to answer, because
Mark, the erosion is very much closely related to landslides. I am actually the chair of the TC on Scour and Erosion. I'm also the acting executive director of the International Consortium of Landslides. So I'm expert on landslides and erosion, both of them. So the landslides and Scour are different disciplines, and both are very multidisciplinary phenomena, requiring multidisciplinary approaches, integrating hydraulics and geotechnics and landslides for geophysics, and the bio also needs to be considered. As Tiago said, the biodiversity also a recent issue of Scour and erosion. So the erosion is closely related to landslides, but a little bit different, in fundamentals.
yes, I know.
both are very rich in physics, but they are closely related. Erosion can cause landslides. So landslides can tsunami, for instance, and tsunami can cause erosion. So the feedback system exists between landslide, Scour, and tsunami or waves. All are linked all together.
Yeah.
So
With the rapid drawdown
yeah.
phenomenon, for example.
Yes.
Okay, so I'm going to conclude, unless you have something to say before we stop recording. Thank you so much, all of you.
Thank you.
This was an amazing episode for joining us from all over the world.
Thank you.
Thank you so much.
Guys.
Thank you.
Thank you, Mark. It was a pleasure.
Gracias.
Bye-bye.
Bye.
Ciao.